All right, so the lesson is about determining a formula, okay? A formula. Let's focus on this. I don't want the actual instantaneous speed at a given time. I want the formula for how to find the instantaneous speed at any time throughout the domain. So what I mean is this: if we were to graph this, okay, let's say we got our graphing calculator and we're going to graph this, and it's going to be 4.9 t squared. We're going to graph it, and okay, so this is representing how fast is the ball falling after seconds. Okay, so this is going to be meters. Okay, so meters from the point that it falls. So this is at the point where it's going to fall, and then as you get further and further from that point, I know it looks kind of upside down, but this is the. Actually, you know what? Let's just make this negative. Let me see. If we make that negative, that actually might look a little bit better for us. Let's try that. Okay. There we go. Oh, how high? How high are we going to be? Let's say we're 100 meters off the ground. Wow, that is huge. Okay, Naomi, you're not going to have much of a chance there. Sorry. Plus 100. Okay, let's see that. Awesome. I have to change my window setting quite a bit. So x maximum is going to go to, let's say, 9. And the y maximum has got to be over 100, doesn't it? Because we moved it up 100. Okay, here we go. This is a little bit better to see. So this is our new function here. And yes, at the 100-meter mark, that's where Naomi jumps off the building. Or sorry, no, you're not going to jump off the building. You're not that type of person, I know. You're going to get pushed off. No, she's going to get pushed off.
By who?
I don't know, by any one of you guys, because you're all rotten. But anyways, so Naomi falls off the building, and look at what happens now. Now, don't think of this as a picture of Naomi falling off the building. All right. What this is the change in meters. This is the height, and this is time. So as the time goes on, her height above the ground changes. Now, if we look at this point right here, soon after, okay, let's go back to the rock, because obviously that's too distracting for you to think about Naomi. The rock, okay, the rock gets thrown off a building, and right here, what is the slope of the tangent? Well, it's about that. Okay, what about the slope of the tangent down here? Would you say it's quite a bit more negative or quite a bit less than negative than shortly after the rock gets thrown off the building? What is the slope? What's the difference between the slope at 1 second versus at 1, 2, 3, 4 seconds? Okay, it's more negative. So we're talking about, if I just draw this real quickly, right? Here we have a slope like this. Here we have a slope like this, right? And what is slope again? For position time graph, so meters, seconds. What does the slope represent again? Velocity. So as you could probably understand, if we throw a rock off a building, it's going to be going a certain speed at this time, but it's going to be going quite a bit faster the closer it gets to the ground, right? Because it's going to pick up speed because of the gravitational acceleration. All right? Now, let's say I just want to know the formula for how to calculate the instantaneous speed. And what we need to do is not to have an actual a value, like a equals 1, but what we're going to do is we're going to let a just equal, basically we're going to let a equal t. So we're going to keep the variable, and so we have a formula with the variable in it at the end, not an actual number. Okay? So we're going to leave t basically in the equation, and we're going to solve for a formula or an expression. That's a better word. An expression for the instantaneous velocity. So this is what it looks like. Okay, trying to erase this. Oh, the erase is fine there. Okay. So the limit as h approaches 0. Let's use that one. of course, we have f of a plus h minus f of a, right? Good idea to just write this formula out over and over again so you memorize it. Write this down. Right now. All over h. Now, h is obviously going to stay in there, but we're not going to put a number in for a. What are we going to do? T. So it's going to be t plus h, because I want t in my final answer. Okay, so if it was x, you'd do the x, or whatever. This one is t here, see? Alright, so we go on here, and we substitute. So this is going to be negative 4.9 times t plus h all squared, minus f of t is just negative 4.9 t squared. Okay? So a couple things that you notice here, we're not going to have just a number here or over here like we used to, right? Because if t was an actual number, we'd have a value. And this is going to have like two variables in it for now. Yep. Oh, you know what? I'm just focusing on my original one. Yes, the 100, sorry. So this is going to be plus 100, and this is going to be plus 100 here. Thank you. Yeah, I forgot about that 100 that we had. So plus 100, thank you. Yeah, I should write that the same color. All right. Okay, so plus 100 over here too, I guess. That's where I need to put it. Okay. Let's rewrite this here. Now, I'll rewrite the whole thing. 4.9 times t plus h squared plus 100. That's the original equation, right, with t plus h in it. And then minus 4.9 t squared plus 100. And that's your original function with just the t still in it. Okay, so yeah, these questions are a little bit long. But again, this one isn't bad because we don't have a fraction here. But what we have to do is we have to expand this out. Or do we? Expand it out? Yeah, we don't have any common factors right now other than 4.9. I suppose we could pull a 4.9 out. That might be a good idea. Remember like we did in this last example? So in the last example that we did, we pulled a 4.9 out right here. Because that's common to both, no it's not. Because it's not in here. Okay, can't do that one. Fine, it's not like the other one. So we'll just keep going. H approaches 0. Negative 4.9. This is t squared plus 2th plus h squared plus 100. And then plus 4.9 t squared minus 100 over h, right? Okay, so we're getting close. I guess we'll multiply this 4.9 in. Should do that. So 4.9 t squared minus, what's that, 9.8 th minus 4.9 h squared. And the 100s are gone. Okay, so I'll let you take a minute to simplify from this step here on. And what you want to realize is that this goes, the h can be factored out here, okay, from the remaining terms. That can be factored out. Now that's going to get divided out, right? You're going to be left with this as your limit here, and now you want to plug 0 in for h, and you're left with negative 9.8t. How many got this? Okay, good. So what this is then, this is the expression for instantaneous velocity of the particle over the appropriate domain. Over the appropriate domain. And of course the domain, I'll let you finish that. Write that down. But the domain, what the domain is all values of x, right? Or of t. So what are the appropriate values of t for this situation, which is like a rock falling off a building? Well, if we go back to our diagram, or our graph, which is still here, appropriate values of t, or the domain, would be from 0, because time, you can't have a negative time. So from 0 all the way till, really, I mean, you could stop anytime after the rock hits the ground, right? Like at the instant the rock hits the ground, this behavior of the rock is not happening anymore. Boom, it stops, right? So the appropriate domain would be everywhere from t equals 0 to t equals 1, 2, 3, 4, about 4.5. And we could solve that, figure that out exactly. But that's what the appropriate domain would be. So what I'm saying is this. At t equals 1, how fast is the rock going? All right, so the instantaneous velocity is negative 9.8 times t, because remember, this is the expression for instantaneous velocity. So it's going 9.8 meters per second in the negative direction. That's at 1 second. Okay? At t equals 2.5, okay, its instantaneous velocity is now negative 9.8 times 2.5. Right? So that's negative 24.5 meters per second. So after 2.5 seconds, it's going quite a bit faster. And it makes sense, right? You know, it'll pick up speed as time goes on. So that would mean that the slope of the line at 1 second would be negative 9.8. The slope of the line at 1, 2.5 right here would be negative 24.5, okay, which makes sense. And it's just going to get steeper as we get closer. All right, how would we find out where the rock hits the ground, or when, sorry? How could we find that out with our calculator? Because you're going to need to know how to do that. Sorry? Calculate the 0, yeah. You want to calculate the root. So you remember how to do that? Second function trace, there's the 0 right there. So second function trace, 2. And then it'll show you this, right? Left boundary, yep. Cursor over so that you're past it. Right boundary, yep. Calculate. 4.5175 seconds. So that's where the rock hits the ground, because that's where the point has a y value of 0. So the height above the ground is 0. All right? When finding a formula or an expression for instantaneous rate of change, do not sub in a value for A. Instead, leave the variable from the function in. Your solution should be an expression including the variable. This variable can then be substituted by any value in the domain to determine its instantaneous rate of change or velocity. So in this case it was velocity, and in this case we substituted t equals 1 over here. We substituted t equals 2.5 over here. And we found, just from the formula, the expression, we found out what the instantaneous velocity was. Okay, so there's the questions I want you to do for today.